In the silent depths of the cosmos, where light itself surrenders to gravity, a singular mystery endures: what truly resides inside a black hole? The question has haunted astronomers, philosophers, and the curious alike for a century, promising answers that could upend our very understanding of space, time, and reality. As we peer into the darkness, the universe whispers a secret that might just break our brains. The story begins with the theory of general relativity, Albert Einstein's 1915 masterpiece that reshaped physics. Einstein described gravity not as a force but as a curvature of spacetime, a fabric that bends under mass. When Carl Schwarzschild solved Einstein's equations for a point mass, he revealed a radius, now known as the Schwarzschild radius, inside which escape becomes impossible. This mathematical surface would later be called the event horizon, the point of no return. But equations alone cannot convey the terror of the horizon. Imagine a star, massive enough to collapse under its own weight, crushing its core into a point of infinite density, a singularity. Around it, space-time twists so violently that all paths lead inward. Light, the fastest thing in the universe, is bent back upon itself, creating a sphere of darkness that swallows entire galaxies. This is the black hole's outer veil, the event horizon, a one-way membrane separating the known from the unknowable. For decades, the singularity remained a mathematical curiosity, a place where physics as we know it ceases to apply. Yet the universe offered hints. In 1964, physicist Roger Penrose proved that once a massive star crosses its horizon, a singularity is inevitable, not an artifact of idealized equations. This theorem cemented the belief that black holes are not mere abstractions but astrophysical realities, existing somewhere in the night sky, waiting to be observed. Observational breakthroughs arrived in the 1970s, when the first X-ray sources, Cygnus X1 and others, were identified as black hole candidates. The detection of high-energy radiation from accretion disks, matter spiraling into the abyss, gave us indirect evidence of the invisible monster. Yet the interior remained concealed, a cosmic veil that no telescope could penetrate, because any signal emitted within the horizon is doomed to be trapped forever. Modern astronomy has taken the mystery further. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, captured ripples in spacetime produced by the merger of two black holes. The resulting waveforms matched predictions from Einstein's equations, confirming not only that black holes exist, but that they can collide, merge, and produce a single, larger black hole. Yet even these violent dances occur outside the horizon, leaving the interior untouched. The Event Horizon Telescope, a planet-spanning array of radio dishes, achieved a different feat in 2019. It captured the silhouette of the supermassive black hole at the center of galaxy M87. The image revealed a glowing ring of hot plasma, bent into a perfect circle by extreme gravity, framing a dark central void, the shadow of the event horizon. This visual triumph confirmed theoretical predictions, but still offered only a silhouette, not a glimpse inside. To venture beyond the horizon, physicists turn to theory. Quantum mechanics, the science of the very small, clashes with general relativity at the singularity. One proposal, Hawking radiation, suggests that black holes are not entirely black, they emit a faint glow due to quantum effects near the horizon. Stephen Hawking calculated that particle-antiparticle pairs can be separated by the intense gravity, allowing one to escape while the other falls in, slowly evaporating the black hole over unimaginable timescales. If black holes evaporate, what remains at the end of that process? Some theorists argue that the singularity dissolves, leaving behind a burst of information, a resolution to the infamous information paradox, which questions whether physical information can be destroyed. Others propose that a firewall of high-energy particles forms at the horizon, incinerating anything that attempts to cross, thereby preserving quantum information at the cost of violating Einstein's equivalence principle. Alternative models challenge the very notion of a singularity. Loop quantum gravity, a theory seeking to quantize spacetime itself, predicts that the collapse halts at a finite, ultra-dense core, forming a Planck star that could eventually rebound, releasing the trapped matter in a cosmic explosion. Similarly, the concept of a gravistar, a bubble of dark energy surrounded by a thin shell of ordinary matter, offers a horizonless alternative that mimics many black hole observations while avoiding a singularity altogether. Even more exotic are the proposals of wormholes, tunnels through spacetime that could connect distant regions of the universe. Some solutions to Einstein's equations suggest that a rotating, Kerr, black hole might contain a ring singularity, opening a passage to another universe. While mathematically intriguing, such structures would likely be unstable, collapsing before any traveler could cross, yet they illustrate how the interior of a black hole could be a gateway to realms beyond our perception. The quest to understand the interior also drives experimental analogs on Earth. Laboratory setups using ultra-cold atoms, lasers, and fluid dynamics can mimic event horizons and Hawking radiation in controlled environments. By creating acoustic horizons in Bose-Einstein condensates, researchers have observed phonon emission analogous to Hawking's predictions, offering a tangible glimpse of processes that would otherwise be forever hidden behind a cosmic veil. Astrophysical observations continue to push the boundaries. The detection of high-frequency gravitational waves from merging black holes could, in the future, reveal subtle signatures of the internal structure, if any, through deviations from the expected waveforms. Moreover, the upcoming James Webb Space Telescope may observe the environment of supermassive black holes with unprecedented clarity, perhaps catching the faint echo of matter that skirts the horizon before vanishing. Yet, despite these advances, a fundamental barrier persists: the very definition of space and time breaks down at the singularity. In that realm, the familiar coordinates we use to map the universe cease to have meaning. Some physicists suggest that inside a black hole, time becomes a spatial dimension and space a temporal one, turning the inevitable fall into an unending journey forward, never reaching an inside in the conventional sense. The implications extend beyond astrophysics. If information can escape or be preserved, it reshapes our understanding of quantum computing, entropy, and the ultimate fate of the universe. Black holes may act as cosmic laboratories where the laws of physics are tested at their limits, offering clues to a unified theory that reconciles the macroscopic world of gravity with the microscopic realm of quantum mechanics. In the end, the interior of a black hole remains a frontier of the unknown, a place where our theories stretch to their breaking point. Whether it harbors a singular point of infinite density, a quantum bounce, a firewall, or an entirely new structure, the answer will demand a revolution in physics. As we continue to listen to the whispers of gravitational waves and chase the faint glow of Hawking radiation, the cosmos invites us to confront a mystery that may indeed break our brains, and perhaps, in doing so, expand them beyond imagination.